Lesson 9, Parallel Plates. Part 1, Introduction to the Parallel Plate System. The parallel plate system consists of two parallel metal plates connected to a battery. When we draw these systems, we're going to draw the traditional battery symbol. This is two lines where the positive side of the battery is always the longer line and the shorter line is the negative side. Because the two plates have a different charge, there's always an electric field between the two plates. What makes the parallel plate system unique is that this electric field is constant between the two plates. This means that the electric field has the same magnitude and direction at all points between the plates. You'll also note that the electric field always points from the positive plate to the negative plate. There are two types of parallel plate problems. The first type is a charged particle shot through a hole in one plate with a velocity directed parallel to the electric field. The particle will experience a force parallel to its motion, and it will accelerate. The second type of problem is when a charged particle is shot into the plates with a velocity directed perpendicular to the electric field. In this kind of problem, the particle takes a parabolic path, similar to a projectile as it travels between the plates. The particle will experience a force that is perpendicular to its motion and move in a parabolic trajectory. This is similar to when you have a particle that's moving parallel to the surface of the Earth, which is perpendicular to the gravitational field. As a result, it experiences a force that is perpendicular to its velocity. And as you know from your previous studies of physics, this particle then takes a parabolic path as a projectile. Similar situation, except for in this situation we're dealing with electric fields and charges instead of masses and gravitational fields. The electric field is the same everywhere between the 2 points. So if I pick a couple points, we'll call one point A, another point B, and another point C, all at different heights between the 2 plates, the electric field at point A will be equal to the electric field at point B and equal to the electric field at point C. It's constant, it's the same everywhere. This is not true for voltage. Voltage is not constant between the 2 plates. It increases with distance. So if you check the voltage at different points, let's call this one voltage 1, a little bit further down, voltage 2, a little bit further down, voltage 3, the potential difference at point 1 is less than the potential difference at point 2 is less than the potential difference at point 3. This is because you're getting more and more of the battery's voltage the further down you go. If you only go to point 1, you get a little tiny bit of the voltage from the battery. If you go to point 2, you get a little bit more, and point 3, you get a little bit more, and if you go the whole distance, you get the whole battery's voltage. It's important to note that there's a difference between positive and negative charges. Positive charges experience a force in the same direction as the field. So if you have a positive charge moving with a velocity in the direction of the field, the particle will speed up. Negative charges experience a force in the opposite direction to the field. So if you have a negative charge with the velocity initially directed in the direction of the field, the particle will slow down. So we'll show this again. If you have a particle that's positive, traveling in the direction of the field, it will speed up. This makes sense because positives are attracted to the negative plate, and so they're going to continue moving faster to get to the negative plate. If we have a negatively charged particle initially traveling in the direction of the field, it will slow down. Also makes sense because the negative particle is repelled from the negative plate, and so it will slow down because it doesn't really want to be near the negative plate. Here are some formulas that will be useful for you when you're studying the parallel plate system. First, there's the voltage and energy formula we learned in Lesson 8, where voltage is equal to the change in energy divided by charge. In this case, the change in energy is often one of two things. The first is the change in kinetic energy, where kinetic energy is equal to 1/2 mv squared. So the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy, or 1/2 m vf squared minus 1/2 m vi squared. And since 1/2 and m appear in both the terms of this formula, we can factor them out and rewrite it as 1/2 m vf squared minus vi squared. The second possibility for this change in energy is change in energy equals work, where work is equal to force times distance. So you could use change in energy is equal to force times distance. The next formula that's going to be useful you learned in Lesson 7. This is the electric field formula. It says electric field is equal to electrostatic force, which is the force that attracts one charge to an electric field, divided by the magnitude of the charge in the electric field. So Fe is the electrostatic force. This could be a force of attraction or repulsion. And Q is the charge in the electric field. And finally, we have a new formula that we can use to calculate the electric field between the parallel plates. Electric field is equal to the change in voltage divided by the change in distance. Watch yourself in these formulas. E with an arrow over top is electric field. V, when it's capitalized, is the voltage or potential difference. In this case, it's often the battery voltage. The change in distance is the separation distance between the plates, which means how far they are apart. Delta D could also be a distance to a point somewhere between the plates. Which would give you a voltage at some point between the plates. So we can analyze the units using these formulas for electric field. Since we have two formulas now for electric field equals Fe over Q, or electric field equals change in voltage over change in distance. We can see in the first one, Fe is measured in newtons and Q is measured in coulombs, so we could use the unit newtons per coulomb for electric field. But we also have volts divided by meters for the second electric field formula. This tells us that we could also use the unit volts per meter for electric field. These two units are equivalent. This is because the electric field unit is a derived unit, and so if you really look at the unit analysis, you'll find that they're actually equal to each other. Part 2. A charged particle shot parallel to a uniform electric field. In this part, we look at the first kind of parallel plate problem. In these questions, a charged particle, we'll call it Q, is shot between the two plates parallel to the field. As a result of the forces on the charge, it either speeds up or slows down. The relevant formulas for these kinds of questions are electric field is equal to voltage difference divided by the change in distance. Electrostatic force is equal to the charge times the electric field. And voltage is equal to change in energy over Q, where change in energy can be given by the change in kinetic energy, which is equal to 1/2 m Vf squared minus Vi squared. Example 1. What is the potential difference between these plates if the electric field is 800 newtons per coulomb? So we have an electric field equal to 800 newtons per coulomb, and we have a change in distance between the two plates of 16 millimeters, which is 0.016 meters. And we're looking for the voltage of the battery, or the voltage between the entire distance between the plates. We'll use the formula electric field is equal to change in voltage divided by the plate separation distance, so that the voltage between these two plates is equal to the electric field times the plate separation distance, which gives us a battery voltage equal to 800 times 16 millimeters, or 0.016 meters, which is a battery voltage of 12.8 volts between the plates. For the second example, we have a parallel plate system where the plate separation distance is 12 millimeters and the battery connected to the plates is 7 volts. What is the voltage halfway between the plates? The voltage is different everywhere between the plates. So we're interested in the halfway point's voltage. Halfway of 12 millimeters is at 6 millimeters. So here's what we know. We know the voltage at 12 millimeters is equal to 7 volts when the plate separation distance is 12 millimeters, or 0.012 meters. We want to know the voltage at 6 millimeters when the plate separation distance is 0.006 meters. The only thing that connects these two is the electric field, which is constant, everywhere between the plates. So if we can determine the electric field between the plates, we can use it to find the voltage at 6 millimeters. Electric field can be calculated using voltage divided by plate separation distance, as long as the voltage and the distance match. That is to say, the voltage at 12 at the distance of 12. So this is 7 volts divided by the plate separation distance at 7 volts, which is 0.012 meters. This gives us an electric field equal to 583 newtons per coulomb. And since electric field is constant in a parallel plate system, the electric field equals 583 newtons per coulomb everywhere, including at the 6 millimeter point. So we can use this electric field to find the voltage at 6 millimeters. The voltage at 6 millimeters is equal to the electric field times the distance. So this is 583 newtons per coulomb times the distance, which is 0.006 meters, which gives us 3.5 volts. This answer makes a lot of sense because if the total voltage is 7, at the halfway distance, half of 7 is 3.5 volts. Example 3. In this example, we have a parallel plate system where the plate separation distance is 2.5 millimeters. The battery's voltage is 2 volts. An alpha particle is shot through a hole in the positive plate at 5.0 times 10 to the 3 meters per second down. What is the speed of the alpha particle when it hits the negative plate? An alpha particle is a positively charged particle. The charge of an alpha particle is equal to 2 times the elementary charge. This is 2 times 1.6 times 10 to the minus 19, which gives us a charge for the alpha particle equal to 3.2 times 10 to the negative 19 coulombs. The mass of the alpha particle is 6.64 times 10 to the negative 27 kilograms. These numbers don't need to be memorized, they're found on your Physics 30 data sheet. Since the alpha particle is a positively charged particle, and it's moving in the same direction as the electric field, it will speed up. A positive particle moving with the electric field will speed up. This means we expect to see an increase in the kinetic energy. First, we need to find the change in energy experienced by the alpha particle as it moves from the positive plate to the negative plate. Since the voltage is equal to the change in energy divided by the charge of the particle, the change in energy is equal to the voltage times charge, which is 2 volts times the charge, which is 3.2 times 10 to the negative 19 coulombs. This gives us a change in energy equal to 6.4 times 10 to the negative 19 joules. From here, we need to use this energy as kinetic energy to determine the final speed. Since change in energy equals change in EK, which is 1/2 m Vf squared minus Vi squared, we can rearrange this to get Vf squared minus Vi squared equals 2 change in EK over m. So Vf squared equals 2 change in EK over m minus Vi squared. And Vf is the square root of this. So Vf equals the square root 2 times the change in kinetic energy, which is 6.4 times 10 to the negative 19, divided by the mass, which is 6.64 times 10 to the negative 27, minus the initial velocity squared, which is 5.0 times 10 to the 3 meters per second squared. This gives us a final velocity equal to 1.3 times 10 to the 4 meters per second. Example 4. In this example, we have a parallel plate system that has a plate separation distance of 7 millimeters and a battery voltage equal to 9 volts. An electron is shot through a hole in the positive plate at a speed of 2.3 times 10 to the 6 meters per second. What is the electron's speed 2.0 millimeters into its journey? The first thing we need to do is find the voltage at 2 millimeters. To do this, we start by finding the electric field. The electric field is equal to change in voltage divided by its corresponding change in distance. We can use the battery's voltage and the plate separation distance of 7 millimeters, which is 0.007 meters, which gives us an electric field equal to 1,285.7 newtons per coulomb. Using this electric field, we can find the voltage at 2 millimeters. So the voltage at 2 millimeters is equal to the electric field times the plate separation distance at 2 millimeters, which is 1,285.7 times 2 millimeters, which is 0.002. This gives us a voltage at 2 millimeters equal to 2.5714 volts. We use this voltage to find the final velocity of the electron at 2 millimeters. Remember, the electron is a negatively charged particle. A negatively charged particle moving in the direction of the electric field will slow down, so we expect to find that the electron loses kinetic energy, or has a lower speed at the end. Voltage is equal to change in energy over Q, so the change in kinetic energy is equal to Q times V. We can find this change in kinetic energy by multiplying the charge of the electron times the voltage at 2 millimeters, which is 2.5714 volts. This gives us a change in kinetic energy equal to 4.11424 times 10 to the negative 19 joules. Be careful. The particle is moving in the direction of the electric field. It's slowing down. It's losing kinetic energy. Since the electron is losing kinetic energy, it has a negative amount of energy. Just like if you were to lose money, your bank statement would have a negative amount of money to indicate the change. The change in EK is equal to 1/2 m Vf squared minus Vi squared. So Vf is equal to the root of 2 change in EK over m minus Vi squared. Vf is equal to the root of 2 times, and don't forget the negative because it's losing energy, negative 4.11424 times 10 to the negative 19 joules divided by the mass of the electron, which is 9.11 times 10 to the negative 31, minus the initial velocity squared, which is 2.3 times 10 to the 4 meters per second squared. This gives us a Vf equal to 2.1 times 10 to the 6 meters per second. Part 3. A charged particle shot perpendicular to a uniform electric field. In this part, we'll look at the second kind of parallel plate problem, when you have a charged particle shot with an initial velocity that is perpendicular to the electric field. The direction of the particle's path depends on the kind of charge it is. If it's a negatively charged particle, it will be attracted to the positive plate, and it will take a parabolic path, like a projectile, but in the direction of the positive plate. This is for a negative charge. If it's a positively charged particle, it will be attracted to the negatively charged plate, and it will dip in the other direction in a parabolic path. Electric fields point towards negative charges. So, if the charge is positive, the electrostatic force is with the field, or towards the negative. If the charge is negative, the electrostatic force will be opposite to the field, which means it will go towards the positive. There are some formulas that will be useful for these kinds of problems. When you have a particle that is initially traveling at a velocity perpendicular to the parallel plates, you separate your problems into a vertical direction and a horizontal direction. In the vertical direction, there are formulas that can be used to find the force and acceleration. Since acceleration is equal to force divided by mass, we need to find the force on the particle pulling it towards the plate. This force is the electrostatic force. And the electrostatic force can be calculated using the charge of the particle multiplied by the magnitude of the electric field between the plates. The electric field between the plates can be found using the parallel plate formula, which is the change in voltage divided by the plate separation distance. Once you have the acceleration, you can use the 5 uniform acceleration equations to calculate other quantities. A equals Vf minus Vi over t. D equals VIT plus 1/2 AT squared. D equals VFT minus 1/2 AT squared. Vf squared equals Vi squared plus 2AD. D equals Vf plus Vi divided by 2 times T. In the horizontal direction, we have constant velocity. The velocity remains the same because there are no forces in the horizontal direction to change the velocity of the particle. When you have constant velocity, you can use the formula V equals D over T. Now, because this is the same particle, just divided into its 2 directions, the time it takes to travel is the same no matter which direction you're looking at. This means that the time in the horizontal direction and in the vertical direction is the same time and can be used interchangeably between the 2 directions. In other words, if you find the time in the vertical direction, you can take it to the horizontal direction and vice versa. In example 5, we have a parallel plate system where the plate separation distance is 8 millimeters and the battery voltage is 9 volts. An electron is shot between the plates at 3.5 times 10 to the 6 meters per second, perpendicular to the electric field, and at a height that is 2.5 millimeters above the positive plate. We know that when an electron or a negative charge is shot perpendicular to the field, it will follow a parabolic trajectory and collide with the positive plate. At what distance will the electron collide with the positive plate? So we're looking for the distance in the x direction that the electron collides with the plate. The first step is to find the electric field between the plates. The electric field between the plates is constant, so if we can find the value of the electric field in general between the plates, we know the value of the electric field everywhere. The electric field can be calculated by finding the voltage divided by the change in distance. This is 9 volts divided by 8 millimeters, which is 0.008. This gives us an electric field between the plates equal to 1,125 volts per meter. Second, we need to find the vertical acceleration. This is the acceleration in the y direction. The acceleration in the y direction is equal to the force in the y direction divided by the mass of the particle, which is an electron. The force in the y direction, or the electrostatic force, is equal to the charge of the particle times the electric field. So this is equal to the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs, times the electric field, 1,125, divided by the mass of an electron, which is 9.11 times 10 to the negative 31. This gives us an acceleration for our electron equal to 1.97585 times 10 to the 14 meters per second squared. Now we're looking for the distance in the x direction along the plate that the electron collides. Since dx equals the velocity in the x direction times t, and we need to find this, dx, we know Vx, which is 3.5 times 10 to the 6 meters per second. In order to solve for dx, we need t. To find t, we look at the y direction, because once you have t in the y direction, you know that you can use it in the x direction. Since we have the acceleration in the y direction, we can use one of the uniform acceleration equations to find t. We can use d equals vit plus 1/2 at squared to solve for t. The original velocity in the y direction was 0. That means that this whole original term, vit, goes away. We have d equals 1/2 at squared. This allows us to rearrange for t. T equals root 2d over a. So t equals the root 2 times the vertical distance the electron travels, which is 0.0025, or 2.5 millimeters, divided by the acceleration in the y direction that we found in previous steps, 1.97585 times 10 to the 14. This gives us time equal to 5.03 times 10 to the negative 9 seconds. You can use this time in the x direction to find dx. dx equals vx times t, which is 3.5 times 10 to the 6, the original velocity in the x direction, times the time we just found, 5.03 times 10 to the negative 3. This tells us the distance along the plate that the electron collides is equal to 0.0176 meters, or 17.6 millimeters.